NASA has shared some new infrared images of the 3I Atlas, showing the object brightening up in a dramatic outburst while exiting the solar system, an unexpected behavior for a visitor that should be fading as it moves away from the sun. Instead of dimming into the background of space, the object released a fresh surge of energy at a point when solar heating was already declining, forcing scientists to confront a puzzling contradiction between theory and observation. If an interstellar visitor can flare at the moment of departure, long after its closest encounter with the sun, what does that reveal about its internal structure, its energy sources, or the possibility that 3I Atlas is far stranger than a typical comet drifting through our cosmic neighborhood? Infrared instruments detected a sudden increase in brightness as the object was already on its outbound trajectory, moving away from the sun and the planets it had briefly visited. The flare was not subtle. It was energetic enough to stand out clearly against expectations, prompting immediate attention from researchers. A flare during solar system exit is not impossible, but it is rare, and in this case the timing appeared especially ill-matched to standard models of cometary behavior. The sun's energy input at that distance should have been declining, not triggering renewed activity. The observation suggested a fresh release of gas and dust, visible primarily in infrared wavelengths that are sensitive to heat and molecular emissions. These data pointed to outgassing involving water vapor, carbon monoxide, carbon dioxide, and organic compounds, materials commonly associated with comets, but not usually expelled so forcefully so late in their journey. In most known comets, peak activity occurs near perihelion, when solar heating is strongest. What NASA observed instead was a delayed reaction, as if something beneath the surface of 3I Atlas had remained dormant until the object was already on its way out. One proposed explanation centers on thermal insulation. If the comet's outer layers were unusually effective at trapping heat, energy absorbed near perihelion could have slowly migrated inward, eventually reaching pockets of volatile material buried beneath the surface. When those reservoirs finally warmed enough to sublimate, they could have produced the observed flare. This scenario is physically plausible, but it relies on specific assumptions about internal structure, layering, and material properties that are not well constrained. It also does not fully explain the intensity or coherence of the outburst. On its own, the flare would already make 3I Atlas an object of interest, but it did not occur in isolation. Since its discovery, the comet has repeatedly challenged expectations, displaying behaviors that, while not individually impossible, collectively strain the boundaries of what is typically seen in natural bodies. This broader context has been emphasized by Avi Loeb, who has cataloged a wide range of anomalies associated with 3I Atlas. His work does not claim definitive answers, but it frames the object as one that deserves unusually close scrutiny. From the moment its trajectory was calculated, 3I Atlas stood out. Interstellar objects are expected to arrive from random directions, with orbits reflecting the chaotic motions of stars within the Milky Way. Yet 3I Atlas followed a retrograde path that lay remarkably close to the plane of the solar system. The ecliptic plane, defined by Earth's orbit around the Sun, represents a thin slice of space compared to the vastness of possible incoming angles. For an interstellar object to align so closely with it by chance is statistically uncommon. This alignment becomes more intriguing when combined with the object's encounters with major planets. During its passage, 3I Atlas approached Mars and Jupiter at distances that were close enough to be noteworthy, but not close enough to result in capture or dramatic deflection. In particular, its nearest approach to Jupiter occurred at a distance comparable to Jupiter's Hill sphere, the region where the planet's gravity dominates over the Sun's. While such an approach can occur naturally, the precision of the alignment has drawn attention because it sits at the threshold where gravitational interactions become dynamically significant. Trajectory anomalies matter because orbits are not random sketches drawn through space. They are records. Every curve, inclination, and encounter reflects an object's past, where it came from, what it passed near, and which forces acted on it along the way. Initial velocity, direction of entry into the solar system, gravitational interactions with planets, and even subtle non-gravitational forces such as asymmetric outgassing all leave signatures in an orbit. When an interstellar object follows a path that appears statistically unlikely or unusually well aligned, scientists naturally ask whether that path emerged purely by chance or whether it reflects conditions or influences that are not yet fully understood. An improbable orbit does not by itself imply anything exotic, but it does signal that the object may not fit comfortably within the simplest models. In the case of 3I Atlas, its trajectory alone does not prove anything extraordinary. However, it establishes an important context. From the very beginning, this object behaved in ways that were unexpected, setting the stage for a broader pattern of irregularities that continue to reveal themselves as observations accumulate. As telescopes tracked 3I Atlas more closely, attention shifted from its motion through space to the structure of the material surrounding it. The coma and tail, normally among the most familiar and well-understood features of comets, introduced a new set of complications. One of the most striking observations was the presence of a persistent anti-tailless stream of material pointing roughly toward the sun rather than away from it. In typical comets, dust tails form as solar radiation pressure and the solar wind push small particles outward, creating the iconic fan or streak that always points away from the sun. Anti-tails can occur under specific circumstances, usually as an optical effect when Earth passes through the plane of a comet's orbit, causing dust lying along that plane to appear sunward from our perspective. Yet in the case of 3I Atlas, the feature did not behave like a brief geometric illusion. It appeared unusually narrow, well-defined, and long-lived, persisting beyond the narrow windows when viewing geometry alone would be expected to produce such an effect. The anti-tail was only part of a more complex picture. Observations taken before and after perihelion revealed collimated jets emerging from the nucleus, sometimes appearing to reverse orientation over time. This kind of behavior suggests a level of organization in the release of gas and dust that is not typical for comets. Standard cometary activity is often chaotic. As sunlight warms the surface, isolated patches of ice sublimate, producing irregular plumes that change as the nucleus rotates and erodes. The resulting jets are usually short-lived and uneven, reflecting the fractured and heterogeneous nature of cometary surfaces. In contrast, 3I Atlas exhibited jets that remained coherent for extended periods, maintaining consistent structure and, in some cases, a striking degree of symmetry. Such coherence implies that the source regions driving the jets were either unusually stable or controlled by internal structures capable of channeling material in a repeatable way. Whether this reflects a layered interior, preferential pathways carved by past activity, or some other physical property is still uncertain. What stands out is that the coma and tail of 3I Atlas did not simply flicker and dissipate as expected. Instead, they behaved in a manner that echoed the earlier orbital oddities, reinforcing the sense that this object was governed by processes that do not fit neatly into familiar cometary patterns. High-resolution images suggested the presence of multiple narrow jets arranged with near-regular angular separation, roughly 120 degrees apart. This kind of symmetry is difficult to produce through random surface fractures alone. It implies either a rotational configuration that repeatedly exposes similar active regions, or an internal structure that channels gas through preferred pathways. While neither explanation violates physics, both require a level of structural integrity that goes beyond the loosely consolidated rubble pile model often used to describe cometary nuclei. Another puzzling aspect was the persistence of jet activity on regions of the nucleus that should have been in darkness. Jets were detected even when parts of the surface were not directly illuminated by the sun, suggesting that internal heat or pressure was sufficient to drive outgassing independently of immediate solar input. This again points toward efficient insulation or internal energy storage, properties that are not well characterized in known comet populations. Physical measurements added yet another layer of complexity. Polarimetric observations revealed an unusually strong negative polarization signal, meaning that the light reflected from a comet's dust behaved differently than expected when compared to most comets. Polarization signatures are sensitive to particle size, composition, and structure. The extreme values observed for 3I Atlas suggest dust grains that are either larger, more compact, or compositionally distinct from those typically seen. The dust itself appeared capable of resisting solar radiation pressure more effectively than usual. For material in the anti-tail to remain coherent while pointing sunward, the particles must have been relatively large or dense. Fine dust would have been quickly pushed away. Larger particles, however, imply either a mechanism for preferentially ejecting heavy material or a composition that favors aggregation over fragmentation. Spectroscopic data showed changes in chemical signatures as the comet evolved. Some expected features weakened or disappeared after perihelion, while others became more prominent later on, including enhanced water production and organic emissions. These shifts are not unheard of, but their timing and sequence did not align neatly with simple heating models. Instead of a smooth rise and fall in activity, 3I Atlas exhibited phases that looked episodic, as if different internal reservoirs were being accessed at different times. Orientation measurements further complicated the picture. The rotation axis of the comet appeared to be aligned in a way that favored sustained sunward jet activity during key observation windows. Such alignment could occur by chance, but it again adds to the impression of fine-tuning. When many low-probability alignments occur together, scientists must consider whether they are seeing coincidence or an incomplete understanding of the underlying physics. None of these anomalies, taken alone, require extraordinary explanations. Nature is capable of producing a wide range of outcomes, and interstellar objects formed under conditions unlike those in our own solar system may naturally differ from familiar comets. It is entirely possible that 3I Atlas represents a class of objects that has simply not been well sampled before. Interstellar visitors are rare, and our observational record is extremely limited. Yet the exit flare observed by NASA refocuses attention on all of these earlier peculiarities. A late-stage outburst implies that something about 3I Atlas allows it to store and release energy in an unusual way. Whether that capacity arises from exotic chemistry, extreme layering, unusual mechanical strength, or some combination of factors remains unknown. What is clear is that simple one-line explanations struggle to account for the full set of observations. As 3I Atlas recedes into interstellar space, it carries its secrets with it. There will be no second chance to send a spacecraft for a closer look, no opportunity to sample its material directly. Scientists are left with telescopic data, models, and comparisons to a handful of other interstellar objects, each of which has proven to be strange in its own way. The flare during exit is the final data point, a reminder that even as the object leaves, it can still surprise. Interstellar space is vast, and the objects that wander into our solar system are shaped by environments we have never visited. Some will fit comfortably into existing categories. Others, like 3I Atlas, will resist easy classification. The flare observed during its departure does not answer the questions raised by its journey, but it sharpens them, ensuring that this interstellar visitor will remain a subject of study and debate long after it has vanished from view.